You see it everywhere, right? Headlines claiming some new drug works or some new program is a game changer. But how do scientists actually decide if something's real or just noise? Well, they use a powerful tool called hypothesis testing. And today, we're going to pull back the curtain and decode exactly how it works. So let's just dive right in. You're reading an article and it says the researchers found a p-value of 0.025. You see that number and you think, okay, that seems small. That must be good. But what is it really telling you? What does that number actually mean? Now, the most common guess, the one that just feels right, is that it means there's a 2.5% chance the whole conclusion is wrong. It sounds so simple, so intuitive. The only problem? It's completely, totally, 100% incorrect. In fact, it's one of the biggest misconceptions in all of statistics. Yup, you heard me right. So for the next few minutes, we're going to bust this myth wide open. We're going to figure out why that common sense answer is wrong and get to the bottom of what a p-value is really saying. And to do that, I want you to forget about the math for a second. Instead, let's think about this whole process like a courtroom trial. A new scientific claim is on the stand, and the data is the evidence. So every trial needs two opposing sides. In statistics, first you have the null hypothesis. You'll see it written as H0. This is basically the status quo, the assumption that there's no effect going on. It's our version of innocent until proven guilty. So for our example, the null hypothesis would be this new supplement Z does absolutely nothing for memory. Then you have the alternative hypothesis. This is the new, exciting idea the researcher is testing, that supplement Z actually does improve memory. This is the claim that's on trial. And check it out, this analogy lines up perfectly. The accused is the new claim, the alternative hypothesis. Our legal principle of innocent until proven guilty is the same as assuming the null hypothesis is true to start. The evidence brought before the court? That's the data we collect in our study. And the final verdict? Well, that's the statistical decision we make. Either we reject the null hypothesis or we fail to reject it. But here's the thing. Just like in a real courtroom, the system isn't perfect. Juries make mistakes. And in statistics, there are two very specific ways our scientific court can get the verdict wrong. Understanding these two errors is the key to this whole thing. This little grid lays out all the possibilities. So if the supplement really does nothing, the null is true, and we correctly decide not to reject that idea, great. That's a correct decision, a true negative. And if the supplement really does work, the null is false, and we correctly reject it, that's also a win, a true positive. But those other two boxes, that's where things get interesting. Let's talk about a type 1 error. In our courtroom, this is a wrongful conviction. It's when we look at the evidence and decide to reject the null hypothesis. We shout, it works. The supplement is effective, when in reality, it does nothing. We found an effect that wasn't really there. It's a false positive. Now, the chance of making this specific kind of mistake is called alpha. And here's what's so important. Researchers decide on this number before they even correct any data. When they set a significance level, usually at 0.05, they are saying, we are willing to accept a 5% risk of a wrongful conviction. That little sliver at the end of the curve right there, that's alpha. It's the line in the sand, our threshold for evidence beyond a reasonable doubt. So what's the other mistake? That's a type 2 error. This is the exact opposite. This is when a guilty party walks free. The supplement actually works. There's a real effect to be found, but our evidence just wasn't strong enough to see it. We failed to reject the null, and a potentially amazing discovery gets missed. It's a false negative. And the probability of that happening, of letting a real effect slip through our fingers, is called beta. Think of it as the risk of being blind to a truth that's right in front of you. If a study has a high beta, it's pretty likely to miss the very thing it was looking for. And obviously, nobody wants that. Okay, so if we don't want to let a real, true effect get away, how do we fight back? How do we build a stronger case? The answer is all about boosting our study's statistical power. And statistical power is exactly what it sounds like. It's the probability that our test will actually find a real effect, if one is out there to be found. In our courtroom, power is the chance that we reach a rightful conviction. It's our ability to correctly see the truth. And the math here is super simple, which is nice. Power is just 1 minus beta. That's it. If the chance of missing an effect, beta, is 20%, then your power to detect it has to be 80%. They're just two sides of the very same coin. And you know, that 80% number isn't just random. It's become the gold standard, the rule of thumb in most scientific fields. You want to design your study to have at least an 80% chance of finding what you're looking for, if it's really there. So how do you get more power? How do you make your case stronger? Well, you've got three main levers to pull. One, look for a bigger effect. It's way easier to spot a 10-foot giant than a 1-inch ant. Two, you can use more precise tools to reduce the randomness in your data. But the big one, the one everyone uses, just increase your sample size. More data is like bringing more and more credible witnesses into the courtroom. All right, we've been through the entire scientific trial. We've set up the opposing claims, we've talked about the risk of getting it wrong, and we've learned how to build a powerful case. Now, finally, we can go back to that original question and understand what statistical significance really is. Okay, let's bring it back. That p-value of 0.025. We know what it's not. It's not the chance that the researchers are wrong. So what on earth is it? Here it is, the real, official definition. A p-value is the probability of seeing the data you saw, or even more extreme data, assuming the null hypothesis is true. That last part is everything. It's a probability that starts with the assumption that the supplement does absolutely nothing. Let's break that down. A p-value is not telling you the probability your idea is right. It's telling you the probability of your evidence. It answers this question. If this supplement were just a sugar pill, how weird is the data we just collected? So a p-value of 0.025 is basically saying, whoa, if this was just a sugar pill, there's only a 2.5% chance we would have seen a result this strong just by random luck. It's a measure of surprise. And this clears up a couple of other huge misconceptions. First, significant doesn't mean important or large. If you have a massive sample size, you can find a statistically significant result that is so tiny it's practically useless in the real world. And second, a result that isn't significant doesn't prove anything as false. It's like a not guilty verdict. It doesn't mean the person is innocent, it just means the prosecution didn't have enough evidence for a conviction. And that is the big shift in thinking. A p-value isn't a final judgment on reality. It's just a statement about the strength of your evidence. Think back to alpha. Alpha is the line in the sand you draw before the trial starts. The p-value is where your evidence actually lands. And if it lands on the other side of that line, then you can call your result statistically significant. So, I'll leave you with this. The next time you see that headline about a significant finding, you'll know what's really going on behind the scenes. And you'll be able to ask the right questions. Not just, is it significant, but how big was the effect? Or how much power did this study have to find it? Now you know how to decode the data for yourself.